Okay, let's get going for the next lecture. I first want to make a couple of announcements. I want to remind you that you are responsible for reading the remainder of Chapter 2, but I want to point out the three sections and how they relate to each other. They are different. They're a change from building upon what we've had in terms of state functions and path functions, but it's a different group. So 2.7 will discuss reversible processes in closed systems. I mean, that's the broad way of speaking of it, but what you're focusing on is two varieties of what we will call polytropic processes. So look out for that phrase, polytropic processes. You're going to have two of them. One is going to be isothermal, a process that is constant temperature, and one is going to be adiabatic, a process that has zero heat flow across the boundary. Okay. Now, the next is section 2.8, which will discuss open systems. So we've shifted from closed systems to open systems, and there it's kind of a different segment, but it's very pragmatic. It's part of kind of a standard group of equipment that we call process equipment that we use all through engineering. And those equipment are listed. You have nozzles and diffusers, which are effectively the opposite of each other. Turbines and pumps, that are again the opposite. One is the same as the other, operating in the opposite direction. And then you'll have a discussion on heat exchangers that have zero work but only exchange heat across the boundary, and throttling devices, which basically are slowing the flow of a fluid. The last section is exploring the thermodynamics cycles. This is where we combine multiple processes together to make a cycle, and the one that we're studying is the Carnot cycle. This is a fundamental cycle in thermodynamics. It's the basis for the best you can get from a heat engine, and that's actually going to use the materials from 2.7 and 2.8 to explore this idea, mainly from 2.7, because what you're going to see is the use of the two polytropic processes, an isothermal process with an adiabatic process, and that will be combined with compression and expansion. So keep an eye on that. We're actually using 2.7's language to really explore 2.9. That's just looking ahead. Now moving on to the lesson. We have Lecture 10, Thermochemical Data for Internal Energy and Enthalpy. I want to remind us all that enthalpy, the term enthalpy, is a state function. It means energy. Just as internal energy explicitly says energy, enthalpy means energy, and enthalpy is the capacity to do non-mechanical work and exchange heat. Whereas we already have explored that the internal energy is the capacity to do work and exchange heat. So both are dealing with Q, exchange of heat, but H really classifies the capacity to do non-mechanical work as well. And we're going to explore that later in this lecture as well. Both of which are state functions, both of which are, meaning by state function that they're independent of path. They are not path functions like heat and work. And a state function is changed by a change in properties. The variables that are measured or calculated are the properties, temperature, volume, and the like. So a change in properties will change a change in state function, which will always be expressed on the left-hand side of an equation. We will do quite a bit simplifying our ideas of a state function in terms of the ideal gas model. The equation for the ideal gas model that we've seen in all of our physics classes is called an equation of state. Now, we didn't call it that before, but that's what it is. So the basic relationship of pressure times specific volume, or pressure times molar volume, is equivalent to the ideal gas constant times temperature, actually points out that we really only need to know the temperature of the system to express a change in an ideal gas behavior, to express a change in the internal energy of an ideal gas. U is only a function of temperature. So if the pressure changes, but the temperature does not, in an ideal gas scenario, the internal energy does not change. Okay? Similarly, H, the enthalpy, or in this case the molar enthalpy, is also a function of temperature only. So keep that in mind, that this ideal gas behavior being only a function of temperature is expressed in the equation of state. We only need to modify the temperature to make the entire energy of the system change. The caution here, and this is basically just to be aware of, that in the textbook, when the gas, like water vapor, which has intermolecular interactions, right? When it does not behave in an ideal behavior, oftentimes it just generally gets coined as a real gas. That does not mean that non-ideal behavior is required for a quote-unquote real gas. We can have atmospheric nitrogen surrounding us right here, behaving as a non-ideal gas, and that gas is real. It just obeys that model. So just be a little bit aware of a language twist here. Non-ideal behavior gets listed as a real gas, but all of our gases are going to behave according to certain models. Now, in that non-ideal gas behavior, like water vapor, we could look exactly at Gibbs phase rule, where we have a pure gas like water vapor, and I can look at my Gibbs phase rule. F is equal to the components. We have one component, one chemical constituent, water, minus the number of phases. We will have one phase, water vapor phase, plus 2. So we will have 2 degrees of freedom, and 2 degrees of freedom is translated into the model for that gas, the equation of state, or the way that we solve the energy change for water vapor will require 2 independent intensive variables, which is why you see on the left side of this in green, the U internal energy is a function of temperature and pressure, or the molar internal energy is a function of pressure and molar volume, etc. You'll see these 2 variables that are required, and we plot them on a 2-dimensional plot quite often. Okay, so let's think about that again, because the Gibbs phase rule brings us back to what would be the state postulate. The state postulate being, for a pure substance, where I have C is equal to 1, all intensive properties, every other intensive property, and thus the actual state function, can be determined from 2 independent intensive properties. And we see that again on page 18. I just want to point out that text, that if we have a system containing a pure substance, its thermodynamic state, and therefore all its intensive thermodynamic properties, can be determined from 2 independent intensive properties. So again, remember that the state postulate is just a kind of a simplified version of the Gibbs phase rule, but it comes into play quite often, so we see it used a lot. Now, I'm trying to bring something together here in page 47 to show you that the state postulate is being demonstrated to you in Chapter 2 and in Chapter 1. So we take Chapter 1 and we use that information in Figure 2.3, where you're going to see that we have an actual path, and we have a change in 2 states. State 1 with T1 V1, State 2 with T2 V2. So the internal energy of the system is actually a function of temperature and pressure. If you look at this, we're going to break that down. If you look at this diagram, you know that the independent variable in this plot is along the horizontal axis. Temperature is the independent variable for the function, and on the vertical axis is the dependent. So we have the independent temperature and the dependent on specific volume, or molar volume, excuse me. That means that somewhere that we're not really expressing, the pressure must have been defined in this system. So unless this is an ideal gas system, but I see that it looks like we have something other than an ideal gas situation in which we will need 2 intensive variables, and so somewhere along this line pressure must have been specified as well. It's implied that this system is constant temperature, and oftentimes pressure gets implied as being constant when it's taking place in the open air at atmospheric conditions. Okay. Each one of these, temperature and pressure, is obviously an intensive variable. If I divide them in half, it does not change inside the system, and each one is independent of the other. If I change temperature, I won't change pressure for a vapor. Now, again, the dependent variable is the molar volume here. But the kind of the bigger picture is that Chapter 1 and Chapter 2 and all of our chapters following are going to be tied together. This is why I say that the actual thermodynamic knowledge that we need to learn ends up being quite easily learned. That the hard part is actually the language and the skills and things like that. But the upshot of this is that State 1 and State 2 can be fully solved with a change in properties of temperature and pressure. And here only temperature is changing, but we express that in that diagram on page 47 as hypothetical paths. So if I change one property, I'm going to have a hypothetical path. I'm going to use step 1a from figure 2.3, where you see that it's a horizontal line, so the molar volume is held constant in the hypothetical path of step 1a. But I change temperature 1 to temperature 2. So I have a thermal change in an isochoric process. Isochoric means volume is held constant. In this case, the actual description of what we're looking for, of that horizontal line of just a change in the temperature of the system, we should know that that's a sensible change in temperature. I'm changing the specific heat, not the latent heat. So I'm only changing the temperature of the system, and I'm not changing the phase of the fluid. So I have a path dependency that described by this arrow that I'm selecting out very specifically for this lecture. That's a path that describes specific heat, and in order to talk about specific heat, we use the phrase heat capacity. When I'm talking about heat capacity, the volume did not change in this equation. And because we already know for a gas that that if I wanted to find out the work, the mechanical, the pressure volume work, I'd have to integrate according to volume, but the volume is already held constant, so no work is done. So this is only a heat-based energy exchange across the boundary. The system itself is closed. It is a closed system, and so I can set up my first law balance with my state function on the left side and my path functions, heat and work, on the right side. But I just defined work as going to 0. So I have a system where volume is held constant, where the change in molar internal energy is equal to heat. The next thing I'm going to do is I'm going to identify that a definition, a mathematical definition, that's that equivalency that you see in the 3 lines. The equivalency, the mathematical equivalency for heat capacity. And this is a specific heat capacity where the system is constrained by volume. The volume does not change, which is why you see the lowercase v. But I've got, that is equal to, this is defined as the partial change in internal energy with the partial change in temperature. If I hold the volume constant, I've already got a definition here where the change in U is equivalent to the change in heat. And so I can express that equivalency here. And so I've got a dq dt that, again, in this case where I have a partial change, a partial change in heat with respect to a partial change in temperature, I'm describing effectively a slope. If I think about slope, and I have a positive Q value, then as I apply energy into the system, the temperature must increase. And when I apply this energy into the system, what I'm actually doing is creating what would be called a constant volume calorimeter. The kind of cooking example that I want you to think about this is boiling an egg, right? we are changing the temperature inside of the egg. There's a fluid inside of the egg. We're changing the temperature from, say, 25 degrees Celsius to 80 degrees Celsius. We're not yet even boiling the water surrounding it. So boiling an egg becomes a kind of a term for what we're actually doing, which is raising the temperature of the egg. But the volume is constant. So I have I'm going to use constant volume heat capacity to answer that question. Heat capacity itself is not a singular term. It's actually an entire function, an entire path or curve. And in order for us to solve that path or curve, we need to use what would be an empirical fit. We would collect data using a constant volume calorimeter, and we would make an empirical fit to that, or a function, a polynomial fit to that data, which you see in equation 2.26. So in the back of your textbook, you will have values of A, B, C, D, and E. Sometimes there's only an A, sometimes there's A and a B and a C, but effectively this is a polynomial expression that will be applied to any number of different real materials for a full range of temperatures in the case of sensible heat change, like before we have any phase change. The function of all of these, why do I have a function, is because I have intermolecular forces occurring. I have molecules interacting with each other in different ways at different temperatures, and so it creates a very complex function. Now, if I were looking at an ideal gas, right, not a non-ideal gas or a liquid or a solid, then the ideal gas model allows us to solve for constant volume specific heat for a monatomic gas just simply as 3 times R divided by 2, or 3/2 R. That's not normally what you're going to find, because most of the time we're looking at specific heat for real materials, in which case we'll go to a lookup table where somebody has done the research, has fit the values to a curve, and we'll look that up and plug those in. In contrast, we have constant pressure systems. A constant pressure system, like I said, in surrounding atmospheres would be like baking a cake, or cookies or cakes. When you cook them from a dough into the actual cake, the volume expands for them. And that equation, again, we start with a closed system. We're assuming that we don't have mass transfer across the system, only energy transfer across the boundary. So I'm going to have a state function du, or delta U, is equal to my heat and work. And when I have a volume change, that means I actually will have work inside of this system. So my pressure will stay constant, but I will have a change in volume. And I will break that down as I will move that change in pressure and volume over to the state function side of the equation so that I've isolated heat. And then I will take delta PV and expand that out. And so you'll see P delta V plus V delta P. However, we know that the pressure stays constant, so the second term goes to 0, and we're left with PdV. Okay? That is the definition to get us to enthalpy. So a change in enthalpy at constant pressure in a closed system, a change in enthalpy is equal to the heat transfer. That's equation 2.28. And so, thus, the definition for the constant pressure heat capacity is partial change in enthalpy per partial change in temperature at constant pressure. And again, there will be a polynomial fit, which is again found by experiment for real materials, gases, liquids, solids, that where we can look up those coefficients in property tables, a sampling of which we have in our appendix, and we will explore that, okay, to solve problems. Now, the next thing in here is to come back to enthalpy and to really draw out one of our reading sections of what are we using enthalpy for in another sense, in this change of volume, but where pressure is held constant. How do we think about enthalpy, or how do we look at enthalpy in another way? And so essentially, let's start with a heat engine, something that's going to convert high temperature heat into work and disperse out some low temperature heat. I'm going to keep the pressure of the system the same. It's going to be a constant pressure heat engine, but I know that the volume will change. So let's draw my system and surroundings of my energy conversion device. Here's my heat engine, as I've shown in notes before, and I'm going to start with state 1. Okay, I'm going to describe a process, so I'm going to go from state 1 to state 2. In state 1 will be described by the properties here: pressure, volume, and temperature. And I could have done molar volume as well. Pressure is going to be held constant, but that means that volume and temperature can change. And so let's look at state 2. State 2, I intentionally drew bigger. So you see that the volume of the system has changed. But if I look at my variable for pressure, you're going to see that it's actually the same. It's P1. P1 is equal to P2, so the pressure of the system hasn't changed, but the volume has. Right? In a closed system at constant pressure, enthalpy accounts for both the change in internal energy and the pressure volume work as the system boundary changes, because the system boundary got bigger, right? That's what enthalpy is valuable for. It's valuable to deal with these constant pressure systems where volume changes and still allow us to solve for the energy balance in the system. Tying together the two, tying together a constant pressure heat capacity with a constant volume heat capacity requires knowledge of some of these equations, knowledge of these equations and how they relate to each other. So I've got a constant pressure system that is defined, where heat capacity at constant pressure is defined in terms of the partial change in enthalpy per partial change in temperature. And I have a definition for the constant volume heat capacity that is mathematically defined as the partial change in internal energy per partial change in temperature. The relationship that becomes really useful here is the definition for enthalpy, or molar enthalpy here. Molar enthalpy is equal to internal energy plus the pressure volume work, or the flow work, as we put it earlier. But PV, or P times the molar volume, all of these three can be then tied together, and we're going to use the ideal gas model first to show kind of how these relate to each other. So I've got my definition for the heat capacity, and I will then insert the relationship for internal energy and flow work, or internal energy and PV work, into the numerator. And then I'm going to break that apart. And you're going to see that I have the partial change in internal energy at constant pressure, right? Which, if I had looked at the other equation above, I would see that normally internal energy partial change is tied to a constant volume, but here we have defined the whole system as constant pressure, so we're going to follow this mathematically through. And then the second term is going to be a partial change in the gas constant times temperature over a partial change in temperature, because we've swapped out PV for RT. And the partial change in temperature over the partial change in temperature is going to be unity. It's going to be 1. So it leaves us with the constant R. So effectively, for an ideal gas, the heat capacity at constant pressure is related to the internal energy by the ideal gas constant. And so I can express the heat capacity at constant pressure is equal to the heat capacity at constant volume plus the ideal gas constant when I'm talking about ideal gases. But even so, in general, every time I look at heat capacities, the heat capacity at constant pressure will always be larger than the heat capacity at constant volume because of that extra pressure volume work that we just saw in the enthalpy note in the textbook. All of this stuff is there. And the interesting thing here will be to try not to memorize these equations, because that's almost ridiculous. But to see the relationships and to be able to build from those relationships to understand the differences here. Okay. So if I think back of the heat capacity in relation to heat change, or the change in heat, the instantaneous change in heat, the heat capacity at constant volume, that would be related to the change in internal energy at constant volume. So if I have the change in internal energy at constant volume, I have a change in Q and a change in work, but my work term went to 0. So I have du is equal to dQ. And I derived that by knowing that there was no volume change, and in this case the flow work would be PdV, and V went to 0. Flip that around and think about the pressure, constant pressure situation, where I have, how does that relate to dQ? Constant pressure is a different scenario where dH is going to be equal to dQ. And dH is equal to dQ because I brought in that pressure volume change into my definition of enthalpy. And so at constant pressure I can define heat exchange exactly relative to a change in enthalpy. And these are going to be my heat capacity terms. And I'm going to use that experimentally because I can put energy into a system. I can have an electrical resistor inside of a cup, and I can know how much energy I'm going to put through that electrical resistor coil, and thus know dQ. And I can have a thermometer in that same cup, and so I can know the change in temperature. And so I have a constant volume calorimeter designed just from a resistor coil that will input energy into my closed system, and a thermometer measuring the temperature change. Similarly, if I then opened off the lid and allowed that liquid or that gas to expand and contract, but I still input the heat exchanger for Q and had a thermometer for T, I could then measure the heat capacity at constant pressure. And people do this experimentally. So I have a constant volume calorimeter and a constant pressure calorimeter that I could be measuring these values for. And that's going to generate those curves, those functions that then are fit with these empirical polynomial fits with A, B, C, D, E coefficients. All right. Everything that we've been talking about has related to gases, okay? Gases that are either behaving in an ideal fashion or a non-ideal fashion. But a solid or a liquid actually does not change very much in volume when you change the temperature. So when I have gases with large volume changes tied to temperature, then I'm going to have a big difference with Cp and Cv. But for solids and liquids, for practical purposes, for engineering purposes, we can often approximate Cp is equal to Cv. So if I can find the Cp data for a solid or for a liquid, I can often just make that equivalent or assume that to be equivalent in a problem for solid or a liquid. It's still going to hold that the real value for the pressure constant heat capacity is going to always be a larger value than the volume constant heat capacity, but experimentally, measurement-wise, within the realm of error of measurement, they're going to be effectively the same numerical value. Okay, the last thing I wanted to talk about was that we've been describing heat capacity in terms of functions. Cp and Cv, they are functions to be integrated along a path. And we know that a path is involved because Q is involved, and Q is a path function. For practical purposes, when I'm only looking at a smaller range of temperatures, say maybe ambient temperature conditions under atmospheric pressure, I can usually get away with using what would be a mean heat capacity or an average value across a range of temperatures. So a practical shortcut that is discussed in the textbook is to use mean values, which would be Cp bar if we're using the pressure-based heat capacity. CP-VAR, the description can be found on page 71. And we know already that the relationship at constant pressure is tied to enthalpy. So a change in enthalpy is going to be the mean heat capacity times the temperature that you are interested in relative to 298 Kelvin, which is basically saying somewhere near 298 Kelvin, we can use the mean heat capacity term. But you still see that that function for enthalpy and heat capacity are broken into the state function change, the process describing a change in state function on the left, and a path function on the right. We're still holding to that format. If I take that equation and I rearrange to solve for the mean heat capacity, then you see in equation 2.33 the mathematical definition of how we arrive at the mean heat capacity. And again, we're doing this mean heat capacity around an area of our heat capacity function or curve that we can approximate in a kind of a linear value and then have a mean value for it. Okay? All right. So in the next lecture, we are going to be taking on latent heats and the enthalpy of reactions. So we spent most of today going through the relationships of heat capacity, and that is sensible heat change, or the specific heat tied to sensible heat change. And we explored that for constant volume, tied to internal energy, and for constant pressure, tied to enthalpy change. All right, I look forward to the next talk. Thanks so much. Have a great day, guys.